I think that this machine might be one of the oldest computer peripherals in the world, and definitely one of the oldest peripherals with support in the Linux kernel via a driver module. So let's talk about what that means, why that's cool, and what we had to do to get there. I wanted this telephone switch to be able to communicate with the rest of the world. If you've seen our other videos, you've seen this machine before, so I won't do a full introduction in this video, but what you need to know is that it's called a panel switch, and this particular one was installed here in Seattle in 1923, and it was in active service until 1974. It and most of the other machines in the museum are all interconnected, so I can place a call from one to the other, and they communicate between each other to pass calls back and forth. But there's another layer here that I don't often talk about. In addition to being able to call each other, many of them could also work with our Asterisk system to use it as a virtual tandem. This lets them make outbound calls to other antique telephone switches on networks like CNET and FreakNet. Now, if you're watching a video on this channel, you may have heard of Asterisk before, but if you haven't, if you've ever used one of those standard desk phones in an office, you've probably used Asterisk without knowing it. It's a free and open source PBX for Linux, and it's most often used to handle SIP calls on VoIP telephones. Now, taking a look around here, we don't really have that many SIP phones, and we don't really use many of the modern telephony features that Asterisk has. To be honest, I don't even think I have the SIP module loaded. But importantly, Asterisk also has an analog telephony module, and we are making very serious use of that. Let me show you an example of how that works. Now, I could place a telephone call directly from the number 1 to number 5 crossbar. But if I dial 11 before my call, I can tell the number 1 to pick up an outgoing trunk to Asterisk, outpulse the called number, and then Asterisk will send the call over to the number 5. Most of the big switches are configured this way, and that allows them to do a bunch of neat tricks, like alternate routing, billing, and other stuff that they wouldn't be able to do all on their own. I can even call my home telephone from here and annoy my neighbors with its super loud ring. Basically, Asterisk is a virtual tandem telephone switch that can enhance the functionality of our real switches and give them capabilities that they wouldn't have otherwise. But there was one glaring hole in this system that I thought I might be able to fix. Asterisk and its associated drivers don't support panel-type reverted pulse signaling. That means that the function I just showed you, where I can send a call from a real switch to Asterisk and have it appear somewhere else, won't work at all with the panel switch. This is because the panel switch uses a unique mode of signaling that, for some unknowable reason, nobody bothered to write support for in modern software. So I set out to do just that. Here's where we're going to start building some understanding. The panel switch is 100 years old, and just like any telephone switch, it has to communicate with itself and with other telephone switches nearby. But it doesn't use MF signaling like I've talked about on other videos. It has its own language called revertive pulse. So let's take a moment to understand how this language works. In the panel switch, the normal user input is from a dial, just like any other old switching machine. But the internal inter-switch protocol is different. This device, called a sender, stores the number you dial and then controls these rods, called selectors, moving them up over banks of terminals until the brush on the selector reaches the terminals that'll connect our call. The panel switch connects calls in several stages, so we actually end up driving a number of these selectors for each call, depending on the particulars of the route the switch is using. Now, these rods are powered by constantly rotating motors, and these clutches cut in the power to drive the selector whenever they're told to do so. The real question is, how does the sender do that? How does it tell the rod where to go? Well, it's actually a type of servo control. As the selector rod is going up, it uses one of these things up at the top to send ground pulses back to the sender for each unit of space that it has traveled. The sender counts these pulses, and when it's counted enough, it sends a command to stop, and the selector stays at exactly that point. In fact, the sender can only send 2 signals forward to any selector, either a closed loop, which means go, or an open loop, which means stop. It's the selector's job to signal backwards towards the sender where it is, and when the sender is satisfied, it opens the loop to tell the selector to stop. This process happens a total of 5 times on regular calls, and it's where the term revertive pulse comes from, since the pulses are sent in the reverse direction back to the sender instead of the sender pulsing forward to the selectors. This method of signaling started dying out in the 60s and 70s, as more and more telephone switches adopted newer protocols that were faster and supported full 10-digit dialing. And when Asterisk began development in the early 2000s, it's pretty safe to say that the software engineers had never even heard of revertive pulse, and so they didn't include it in the list of supported protocols. Now let's fast forward 100 years and talk about the architecture of our Asterisk system. Just a warning, this is about to get pretty computery, so if that's not your thing, just stick with me because I think the payoff is pretty cool. All of our switches are linked together directly, but they also have links into our D4 channel bank. This channel bank contains several spans of T1 equipment, each of which takes 24 analog telephone channels, scans each channel 8,000 times per second, turns that into a PCM audio stream, plus some signaling bits, and multiplexes them onto a completely digital link between 2 points. Its original purpose was as a carrier system, very similar to the kind we discussed in the last video on phreaking. You can connect a number of inter-office trunks to this system, combine them all together, and send them in a digital format to a distant telephone office using only 4 wires. Each channel has a removable card, and that card is designed specifically for the form of signaling that the channel is designed to work with. The cards just read in the real signaling states on each channel and turn those states into bits that are transmitted over the T1 protocol. And on the other end, an equivalent card takes the digital signaling states that it got from the T1 stream and it converts them back into 48-volt signals that the telephone switch expects. On the other end of our T1 system is this regular old Dell PC. Inside, it has a bunch of boring computer hardware, but in particular, it has a T1 card here in a PCI slot, which pretends to be a virtual D4 bank. The real D4 bank has no idea that it's talking to a computer, as the computer speaks the protocol that the D4 is expecting to hear. You can almost think of this as a huge adapter, where you have a real telephone switch on one end and a computer on the other, and all of the logic levels are read in, timed, and translated into something that we can send over 4 wires into an RJ45 port. Inside the computer, we have a bunch of software. At the very bottom is the Linux kernel, which has a driver for the T1 card. This driver is called Dottie, and its job is to take the signaling bits from the T1 stream and pass them up to Asterisk, which lives in user space. Asterisk has a module called ChanDottie, which speaks to the kernel driver and handles the data and signaling logic, and also passes the audio stream through so that the 2 callers can hear each other. All of this just allows the computer to function as a virtual telephone switch, which slurps up the digital bit stream from the T1, handles the signaling accordingly, and can receive and make calls to the real switches, and they're none the wiser. Except for the panel switch. If I plugged in this RP card and I tried to send a call into Asterisk via the kernel driver, the software just wouldn't know what to do with it. Nor would it be able to place a call into the panel office because incoming calls to the panel office require that revertive pulse signaling system in order to move the rods to connect the calls. What I had to do was create a way for the computer to function as a virtual panel switch that sent and received all of the expected signals to the real panel switch, so it can make and receive those calls to and from the computer. I want to restate here that we aren't simply trying to dial calls into the switch like a subscriber would. We can do that already, and computers are actually already pretty good at pretending to be telephones. What we're trying to do is link the panel office trunks to the computer so we can speak to the computer like we would any other panel switch. So this is where I get a bit cheeky. I've never been great at writing software, and I didn't know the C programming language. So I asked some other folks if they could write the driver code to speak revertive pulse. They wisely said, I could, but I won't. They obviously knew something about this that I didn't. So, being a stubborn idiot, I took a look at the analog signaling code and thought, okay, I can probably figure this out enough to write reasonably safe code that works reasonably well, and I can learn C in the process. So why not? But as I delved deeper and deeper into the software, I found that I had my work cut out for me. This is tens of thousands of lines of code, and while most of it appears to work from the user perspective, inside it was clearly written with some very weird assumptions about how telephony works. Now, I'm not a professional software engineer, I am barely an amateur. So it's not really okay for me to go around saying bad things about other people's code. But even I could see that this was full of dead ends, thousands of lines of duplicate code, weird spaghetti mazes, and bad ideas about design. So instead of diving right into the asterisk and dotty code, I wrote my own sender and selector code in C, which just takes user input from the command line and pretends to be a real panel switch. This was a long way from the real-world application I was going for, but it at least helped me develop my theories around how this should ideally work. Speaking of the real world, once I finally started writing code for asterisk and dotty, I realized that I was going to have to make some big changes to get around some of the assumptions that were made by the original developers. The first one was that all of this software heavily assumes that signaling is going to be in the forward direction, which is reasonable, but it's all architected with those assumptions baked in. But that won't work with revertive pulse because, as we now know, the signaling is sent backwards from the endpoint back into the sender. Now, it could be refactored to remove those assumptions and make it much more agnostic about signaling, but instead of spending 6 months refactoring everything before I could even start on my own project, I just decided to break out of the normal code flow once revertive pulse started and move into my own functions, which I knew would work properly. I defined some new signaling types and set up the config file parser so that I could tell Dotty about them. When Dotty sees signaling bits on a revertive pulse channel, it passes them off to my signal handlers, and I get to control the show from there. These are the two main functions in the driver that are responsible for handling RP. One is a sender, which tells a real selector where to go, and the other is a selector, which listens to a real sender and pretends to be a rod that's moving up over terminal banks. Using these two abstractions, I could both place calls into and receive calls from the panel switch. What really helped me with this were the CDs, or circuit descriptions, for a real sender and a real selector. These accompany the schematics and detail step by step how the actual circuit functions. In my code, I reference specific sections and paragraphs to give myself pointers back to the circuit descriptions, which are my single source of truth. I want to take a quick step back here to point out something else that was really helpful to me as I abstracted this away into code. Newer switches that came after the panel, like the number 1 crossbar, had to be backwards compatible with the panel, so even though they didn't have rods that moved up over terminal banks, they still had to pretend that they did in order to communicate with all of the existing panel switches out in the wild. So they had special circuits that pretended to be selector rods. When the panel switch had to communicate with one of these newer ones, it sent the same commands to start and stop the selectors. But in reality, The circuits on the other end were just generating pulses and counting and storing the number of pulses they generated. Then they did some math to convert those pulse counts back into actual telephone numbers and connected the calls. The panel switch didn't know and didn't care what the newer machines were doing, just as long as they signaled back appropriately. In these newer switches, revertive pulse became one of the first real protocols, where the signaling was completely disconnected from the physical reality of the switch. So while I was writing this code, it was actually really helpful to me to read about the 1940s era circuits that pretended to be selectors, since this ended up being a lot closer to what my code was doing. So anyway, I was pretty excited when I got my sender working for the first time. This next clip is the first time I tested my code with an actual switch, and I'm placing a real phone call into the computer and asking the computer to call into the number 1 crossbar using revertive pulse. In true Sarah fashion, my first official act was to blow a fuse. Whoop. But once I fixed that, I was absolutely over the moon the first time it actually worked.
Yes. There's no one there, but I don't even care.
The final bit of error handling that I had to do was to figure out how to deal with badly behaved users. This was a hard one for me because when I test my own code, I have an unconscious bias that makes me want to stay on the happy path. But in order to make something truly robust, you have to try and break it. So after all the months I spent writing this, I spent several more weeks just hammering it to pieces. And let me tell you, there are some interesting ways that this breaks. One situation that really took me a while to solve was what to do when a caller hangs up while signaling is happening. In a panel switch, if you hang up while dialing, the sender and the selector that's under control have to do a little dance to unwind their internal states so that they can start cleanly on the next call. Otherwise, you may have a selector that's stuck in the middle of a bank somewhere, or a sender that's stuck expecting more signaling to come in and that just never happens. In the Dottie kernel module, hangups were ordinarily pretty simple. You just hang up the channel, reset some variables, release some memory, and you're good. But in this machine, you cannot just hang up. You have to keep the loop closed, but arrange your pulse counter to never be satisfied. This causes the selector to be driven to the topmost terminal of the bank, which returns a polarity reversal to the sender, which then opens and closes the loop once more to advance the selector's state machine and engage the downdrive clutch. Doing all that in code involves some clever timing and feedback to make sure that it all happened like it was supposed to. And I had to emulate these functions from both perspectives, so that a real sender and a real selector would work like they're supposed to. What made things harder still was that there's actually 2 cases in which a selector will return a polarity reversal to the sender. One case is when it reaches the end of its travel, and the polarity reversal acts as a limit indicator. And the other case is when the selections have finished successfully and the call's about to be connected. The difference between these 2 cases is whether or not the sender has completed all relevant selections. So I had to observe the polarity reversals and act accordingly depending on whether they indicated a problem or indicated a successful completion. Anyway, I can now say that it works. And the result is that the panel can place a call into the Linux computer, and then the computer can route it wherever it needs to go, including back into the panel switch. This next clip may not look exciting, but it's absolutely magnificent to me. Here, I'm placing a revertive pulse call from the panel switch into the computer, and then the computer is using revertive pulse again to drive the panel selector to the called line.
7, 2,
3,
3, 5,
5, 6, 7, 8. Those are some fun noises.
I am insanely proud of this, both because I love this machine and I got to build something cool while learning a new skill. By the way, massive thanks to fellow volunteers Matt and Astrid, because without their input and guidance, this would not have happened. They're both actually professional programmers who do this kind of thing for their job, and they knew a lot more than I did, and were kind enough to nudge me in the right direction whenever I got lost. I'm not sure that this code has any wider application outside the museum, since I don't know many other people with a panel switch. There's museums in Europe and New Zealand that have switches that speak a version of this language, so my code could probably be adapted to work with their machines as well if they wanted it to. I also don't have a lot of hope that this will ever get merged into the main branches of Asterisk and Dotty. It would be cool if it did, but it's pretty unlikely. They're out to make money after all, and this probably won't get them any new contracts. But the panel switch is now probably the oldest Linux peripheral in the world, and that's cool. I hope you liked the video. If you did, please remember to click all of the relevant buttons to tell YouTube that we're cool and share it with your friends. Leave a comment below, and I'll try my best to answer any questions you may have. And see you next time.